In this lesson, you will learn how to find the number of permutations of the elements of a set. And what we're doing in this lesson is going to be the basis for probability, because for probability, we need to know how many total possible outcomes are there. And with permutations, we are trying to determine, in these specific scenarios, how many outcomes do we possibly have. And a permutation, by definition, is an arrangement of given elements. So we're counting the number of ways that we can arrange certain elements. And with a permutation, the order makes a difference because we're arranging them. So for example, if you had A, B, and C, and you're asked how many permutations are there using those letters. Well, what I do is I can arrange them in multiple ways. So we can arrange it where we have A, then B, then C, or BAC. We could have C, then A, then B, or ACB, BCA, or CBA. So if you count all of those permutations, or all of those arrangements, we would find that we have 6 permutations. So this example is pretty straightforward, and we could just list out all the possibilities. But our objective is to get to the point where we don't need to list them out, but that we can use different concepts or principles so that we can just multiply instead. So this example would be pretty quick to do by listing, but I'm going to show you now the thought process that we need to find permutations quickly. So using the same example, we know that we have 3 letters to choose from, and we're arranging these 3 letters. So for the first letter, the first option that we pick, we can pick from any of these 3 letters. So for the first letter, we have 3 possibilities that we can put there. But then once we put one of the letters there, say we pick the letter A, for example, now for the second spot, we only have 2 options remaining. We have a B or a C. So letter 2 has 2 options. So now we've used 2 letters. Let's say we use A, and then now we use up to C. Now we have 1 letter remaining for that last spot. So using the fundamental principle of counting, for every letter we choose for the first option, we have 2 letters for the second option. And for both of those, we have 1 letter for the third option. So then we multiply those together to get 6 permutations, which is the same as if we were to count them, but this will save us time, especially with bigger problems. So using this concept now with 5 letters, yes, we could list all of the possibilities of ways to arrange these letters, but that's going to take a long time. So what we want to do is use the same thought process, where we pick one of the letters to put here in slot 1. So we pick one of the letters, and we have 5 to choose from. So we have 5 options for letter 1. So now we've used one of the letters, and now we have 4 remaining. So letter 2, there would be 4 options. So we pick another letter, and now we have 3 options remaining for letter 3. So once we use the third letter up, now we only have 2 options for letter 4. So now we've used 4 letters, and we have 1 letter remaining for that 5th spot. So what you have would be 5 times 4 times 3 times 2 times 1, which would give you 120 permutations. Now notice, this would be very tedious and difficult to list out by hand. So therefore, we want to use this principle of the counting and with permutations in order to calculate quicker. Now we have another term we need to know called factorial. What factorial is a quick way to express what we just did. We saw before that the numbers were descending. We had 5, then 4, then 3, then 2, then 1 that we multiplied together. Instead of writing it out like that, we can use what we call factorial. So for example, we see here 2 and then an exclamation point. This exclamation point is what we call factorial. And yes, this does have mathematical meaning here in the context of probability, where what this means is we take the 2 and multiply by every number that proceeds. So 2 times the 1. 3 factorial would be 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial is 6, 5, 4, 3, 2, 1, multiply together. And we could keep going for 7 factorial and 8 factorial. And this goes on, for any size of number. And here, notice the pattern. Okay, the number that we're taking the factorial of, we multiply by that number, and then every number that follows it until we reach 1. And then a little side note, if you have 1 factorial, that would just be 1. And we also can find what we call 0 factorial. And this, just for the sake of the math working, this needs to be 1. So it's kind of like the concept of raising something to a 0 power, where anything to the 0 power is 1. This is kind of the same concept, sort of, where 0 factorial, we just know that to be 1. Now looking back at the previous example, where we had the letters A, B, C, D, and E, and we're trying to determine how many permutations there are using these letters. Well, what we said before was that we had 5 times 4 times 3 times 2 times 1. But what we can do now is, instead of writing out the 5, 4, 3, 2, 1, I could use factorial to represent the same thing, where I can write 5 and then the exclamation point after the 5 to represent 5, 4, 3, 2, 1. Now let's look at an example where we are trying to determine how many ways the letters in the word monkey can be arranged using only 4 letters at a time. So we see here the key word arranged, which would imply that we are dealing with a permutation. But notice here we only are taking 4 letters at a time. So what we have are 4 letters. So for the first letter that we put, we have 1, 2, 3, 4, 5, 6 options in the word monkey. There are 6 letters to choose from for this first option. So we have 6 letters to choose from, and now we use one of the letters up, and now we're left with only 5 letters for the second option. So now we've used 2 letters. We have now 4 letters remaining for letter 3, and now that we've used 3 letters, we now have 3 letters remaining for the 4th letter. So you multiply all of those together, and you get 360 permutations. Now notice this is kind of like a factorial in the sense that we are starting with a number, multiplying it by the number right beneath it, then multiplying by the next one and the next one. But notice there is no times 2 and then times 1 to make this a factorial. But it's kind of the same idea. So here in probability, we can write this in a shorthand manner. So instead of writing this with a factorial sign, because it's not a factorial, what I can do is I can say that we have 6 options to choose from. So here we see a 6, and we are picking 4 letters at a time. So here's where the 4 comes from. Then we put a P here to represent permutation. So we'd say that this is 6P4. And that is the same way of saying what I just have written up above. Now, this is helpful because there are times when you have a lot of different options and you don't want to have to write out, 10 times 9 times 8 times. It's going to be much quicker if you can just write it like this with 6P4. So in general, we can say NPR, meaning we have n objects taken r at a time. In this case, we had 6 objects taking 4 at a time. Now, if you are given this notation, 6P4, and you don't have a context given to you, and you're trying to calculate what is 6P4, well, I could think through it this way, where I have 6 options to choose from, and I'm taking 4 at a time, and I can have 6 times 5 times 4 times 3. I could think through it this way, but another way I can think through this will be as follows. What we can do is we can take the 6 right here, make that a factorial, then divide that by the 6, then subtract 4, and take the factorial of that. Because 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. 6 minus 4 factorial is 2 factorial, or 2 times 1. So then, using my laws of fractions, I can cancel these out, and I'm left with 6 times 5 times 4 times 3, which would be the same solution that we had before. So notice we get the same thing doing it this way with factorial, or in the previous way by thinking of it as 6 times 5 times 4 times 3. So make sure you can think through it all these different ways, where we can think through it with 6, 5, 4, 3, or with the factorial to get to the correct answer. Here's another example where now we are just given 8p5. So 2 ways to think of this. We have 8 items, we're taking 5 at a time. So we have 5 that we're taking at a time. We have 8 options for the first, then we use one up, now we have 7 for the second, then we have 6 for the third, then 5, and then 4. So you could think through it this way and have 8 times 7 times 6 times 5 times 4. But the other way we can think through this would be with factorial, where I take the 8, make it a factorial, and then subtract 8 minus 5 and make that a factorial. So 8 minus 5 is 3, so we have 8 factorial over 3 factorial. Well, 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1, all multiplied together. 3 factorial is 3 times 2 times 1. And then we can cancel the 3, the 2, and the 1 to leave me with 8 times 7 times 6 times 5 times 4, which notice is the same thing that we had up here. So when you multiply those, you'd get your answer being 6,720. Now here's an example with actual context. We are told that from a set of 8 different books, 3 are to be selected and arranged on a shelf. And the question is, how many arrangements are possible? So we know that we have permutations because we see the keyword arrangement. And we have 8 books. We're taking 3 at a time. So it's going to be 8p3. 8 books taking 3 at a time, and p for permutation. So from here, all we do is solve this, where we have 8 factorial on the top, and then 8 minus the 3 factorial on the bottom. So we have 8 factorial over 5 factorial. So 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1. 5 factorial is 5, 4, 3, 2, 1. I can divide out the 5, the 4, the 3, the 2, and the 1 to leave me with 8 times 7 times 6, which would equal 336. The other way to think through this would be, we have 3 that we're choosing at a time. So we have 3 blanks, 3 spaces to put the books. And for the first space, we have 8 options because we have 8 books to choose from. So we have 8 books there. Once we use a book up, now we have 7 remaining for the second spot. And then from here, we've used 2 books. We only have 6 books remaining for the third spot. So we have 8 times 7 times 6, which is the same thing as if we were to use the factorial. Now the question is going to be, what if you have repeat letters? So here we have A, and B, and the question is how many permutations can be made using those 3 letters? So just like before, I can list out all the possibilities, where I could have AAB, ABA, BAA, or AAB, ABA, or BAA. Where notice the red letter is the one A, and the other white A is the other A. Now, looking at this, we have 6 possibilities, 3 times 2 times 1. We have 6 possibilities, but notice that some of these are repeats. So here we have repeats, and then here are repeats, and these are repeats. So even though, yes, we moved the letters around, where this A was first here, and then we moved it to the middle spot, that's still the same arrangement, because the 2 A's are actually identical. So to divide out those repeats, what we do is we see how many letters are being repeated. So we see we have 2 letters being repeated. We have an A and an A. So the question now is, how many ways can I arrange these 2 A's to account for those repeat variations? Well, I have 2 letters. For the first blank, I have two options to choose from. And then once I use one of the letters up, I have one option remaining. So what I have is going to be 2 factorial, or 2 repeats I need to account for. So I divide by 2 factorial, so I get 6 divided by 2, which gives me 3 possible permutations. So the concept is this. For every letter we have repeated, we need to divide by that number factorial. So here we have 2 letters repeated, so we divide by 2 factorial. If we had 3 A's being repeated, I divide by 3 factorial. And if I had, for example, A, and then B and B, and the question is how many ways can I arrange this? Well, same concept. I have 1, 2, 3, 4, 5 letters to choose from. So I have 5 factorial ways that we can arrange them. But then divide out the repeats. So here I have 3 A's being repeated, so I divide by 3 factorial. But I also have 2 B's being repeated, so I divide by a 2 factorial. So you look at each letter separately. Don't combine them to say, oh, I have 5 letters that are being repeated total, but don't divide by 5 factorial. We look at each letter separately. So we have 3 factorial divided by 2 factorial. So here's another example where now we have the question where how many ways can the word none, can the letters in the word none be arranged? Well, I have 4 letters in the word. So 1, 2, 3, 4 letters. First option, I have 4 letters to choose from. Once I use one up, I have 3 letters. Once I use 2 letters up, I have 2 letters remaining, and then 1 letter at the end. So what I have is 4 factorial ways to arrange them. But then I need to divide out the repeats. We have 2 n's being repeated, so I divide by 2 factorial. So my solution is 4 factorial divided by 2 factorial. So I have 24 over 2, which gives me 12. Here's another example. How many ways can the word Hawaii be arranged? So we have 3, 4, 5, 6 letters. So we're arranging 6 letters, so I have 6 factorial. And then I divide out the repeats. I have 2 A's, so I divide by 2 factorial. Then I have, I have 2 I's as well, so I divide by another 2 factorial. So my solution would be 6 factorial divided by 2 factorial times 2 factorial. Well, 6 factorial would be 6, 5, 4, 3, 2, 1. 2 factorial is 2 times 1. We have 2 of those. So we can simplify, and we have 2 times 2, that gives me 4. And the 4 down here can cancel with the 4 up here. So I have 6 times 5 times 3 times 2, which gives me 180. One more example. We have the word beekeeper, and the question is, how many ways can I rearrange these letters? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters to arrange. So I have 9 factorial permutations. But then I divide out the repeats. Here I have 1, 2, 3, 4, 5 E's. So I need to divide by 5 factorial. So I have 9 factorial divided by 5 factorial. So 9 factorial is 9, 8, 7, 6, 5, 4, 3, 2, 1. 5 factorial is 5, 4, 3, 2, 1. The 5, 4, 3, 2, 1s can cancel on the top and the bottom. So I have 9 times 8 times 7 times 6, which gives me 3,024. And that concludes our lesson for today. We will see you next time.